Alright, here are the solutions to the exam prep problems. I'm going to put up the answers to the first good bit, and then I'll go into a little more detail on some of the solutions for the AP exam prep free response questions from the end of the Chapter 7 review exercises. Alright, here are the problems that we worked on. I want to stress a couple things. The first is problem number 67. Don't do that one. That is actually going to need an integration technique that we haven't learned yet. And then also want to stress how helpful the AP free response questions that we did both in 10.07 and the ones that we've done in class are going to be. That's the best practice that you can possibly get, and redoing those problems is actually very beneficial. Alright, with that being said, let's take a look at the answers. Here are the solutions to 1 all the way through 66. A couple things that I want to say here. Here are the slope fields for 37 and 38. These here are all slopes of 0, your horizontal lines. So are these here. And you should be able to tell that these are slopes of +1, -1, and then here you can see that the slopes here are negative, the slopes here are positive. And you can see the relative steepness. You should be able to. Number 66, Part A, is something that we've done already on those AP free response questions, finding a line tangent to a curve at a given point and using that line to approximate the function at some other point a little bit down the road. All right, here's problem 68. We have a population of wolves where T is measured in years starting at 0. And we're told that the population is increasing at a rate directly proportional to 600 minus p, where the constant of proportionality is k. So if you remember when we discussed exponential growth, the constant of proportionality is that constant that we're multiplying by the variable here. And in this case, we're told that it's proportional to 600 minus p, not just p. So it would be k times 600 minus p. So this is our differential equation. In part A, we're given an initial condition that p of 0, population at time 0, is 200, and so we're going to find p of t. Notice they tell you that it's going to be in terms of k and t, meaning you're not expected to solve for k. You're going to leave it as a constant. So I'm going to separate my variables. That gives me dp over 600 minus p equals k dt. Take the antiderivative of both sides. On the left side, I'm going to make a u substitution, and I stress how important it is to actually follow through the u substitution, and this is an example why. My u is 600 minus p, which means that du is equal to negative dp. Now, that means I need to multiply by a negative on both sides so that I have an expression just for dp, the differential of p, which gives me a negative du. So when I go back and make my u substitution, I'll now have this negative du, factor the negative out. So it'll be negative the antiderivative of du over u, which is of course negative natural log of the absolute value of u. And the reason it's so important to do this is it's very easy to forget this negative out front, and doing so leaves you with a completely wrong answer. So substituting u back in, I now have a negative natural log of the absolute value of 600 minus p is equal to, and here the antiderivative of 1 dt is simply t, so k t plus c. Using my initial condition to solve for c, I get c is equal to negative the natural log of 400. Plugging that back in, I can now multiply by a negative on both sides, and the reason that I do this is I need to isolate p. So when I raise e to this power, to the power of natural log, I don't want a negative here. So I'm going to multiply by a negative on both sides, and doing so will now give me negative kt plus natural log of 400. Now I can raise e to the power of both sides, and in doing so I'm going to end up with 600 minus p, and I can take away the absolute values because 600 minus p is always going to be greater than 0. Notice that my population is going to start at 200, and if I look at my differential equation here, I can see that as p approaches 600, that's where it's going to, the slope is going to approach 0. And so it'll be impossible for my population to ever be more than 600. It's important to note, and if you're confused by what I'm saying, go ahead and make a slope field here and notice that the slopes are going to be 0 when p is 600. So you can see that 600 minus p will never be greater than 0. So here I have 600 minus p is equal to, and now e to the negative kt times e to the ln 400, because I'm adding in the exponent. E to the ln of 400 is 400, so I have 400 times e to the negative kt. And then solving for p gives me p of t is equal to 600 minus 400 e to the negative kt. Kind of a lot of work, but you can see that it makes sense when you're all said and done, that it satisfies your initial condition. If t is 0, then you're going to have 600 minus 400, which is 200, my initial condition. All right, want to point out a couple of things here. It's important to note that we multiplied by a negative. That's a good thing to be able to do, and also to understand why 600 minus p is always going to be positive. You can look to your differential equation to see if it'll ever be possible for p to start at 200 and pass 600. And since it isn't, you can say that 600 minus p will always be positive. All right, moving on to part B. If p of 2 is equal to 500, find the value of k. And notice if I use that point, I can set t equal to 2, and that allows me to solve for k, because now I'll have one variable, k, that I need to solve for. And so what I'm going to do is I'm going to subtract 600 on both sides and divide by 400. That'll end up with 1/4 on the right, and I'll take the natural log of both sides. So I have the natural log of 1/4 on the right, and the natural log of e to the negative 2k on the left, which of course is just negative 2k. So solving for k by dividing by negative 2 on both sides gives me natural log of 1/4 divided by negative 2, which is 0.693, or actually the natural log of 2 if you were to just simplify it that way. So that is the value of k, and now I can actually write out my particular solution with k involved, which is helpful because in part C I want to find the limit as t approaches infinity of p of t. So setting this up here, what this really is saying is, what is the population going to be as t approaches infinity? Meaning, as I look really far down the road, what is my population going to be getting closer to? So I'm taking the limit as t approaches infinity of my function here, and notice that the limit of 400 e to the negative 0.693t is going to approach 0. Because I have e to the negative something, I can move that into the denominator and make the exponent positive. So to show you what I mean, I could rewrite this as 400 over e to the 0.693t. And what's going to happen here is that as t approaches infinity, this is going to become infinitely big. So 400 divided by infinitely big number is going to approach 0. And therefore I'm going to be left with 600. So the limit as t approaches infinity is 600. A really nice way to see this is to sketch the slope field. So if you look back at your differential equation, you had k times 600 minus p, which means that your slopes are going to be 0 when p is 600. So you notice that I've written those here in green. If I start with an initial point at 200, so when t is 0, 200 here, the slopes are positive, they're all positive, and that means I'm going to be moving towards 600. But I can never pass 600 because the slopes are all horizontal here. So my function will look like this, and I can see that as t approaches infinity, my value of my population is approaching 600. So again, using the slope field can be really beneficial. All right, in 69, we are parachuting with a velocity given by v of t in feet per second. This skydiver is beginning their parachute trip at t equals 0, and the velocity satisfies this differential equation right here. We also know that the initial velocity is negative 47 feet per second. That should make sense when your velocity, when you're traveling downward, as you are when you're parachuting, we use a negative to represent the direction that we're traveling. In part A, we're going to find a solution, a particular solution for v, and we're going to do that by using separation of variables. So I'm going to end up with dv over v plus 17 is equal to negative 2 dt. I'm going to take the antiderivative of both sides. I'm going to make a nice little u substitution here. Makes this pretty easy. So the left side is going to be the natural log of the absolute value of v plus 17, and the right side will be negative 2t plus c. Use the initial condition. Solving for c gives you natural log of 30. So I'm left with natural log of the absolute value of v plus 17 is equal to negative 2t plus natural log of 30. I'm going to raise e to the power of both sides of my equation, which allows me to get absolute value v plus 17 is equal to 30 e to the negative 2t. Now, what is v plus 17 going to be? Notice that my initial velocity is negative 47. Well, that means if v is negative 47 plus 17, that's a negative number. Also, think about your differential equation. How is the velocity changing? Well, if you start out with v at negative 47, you'll have a negative number times another negative number, which is positive. So you can see that your velocity is going to be increasing a little bit, but it's starting at negative 47. What that tells you is that it's going to be increasing from negative 47, and where is it going to stop? Well, you know that your derivative of v is going to be 0 when v is negative 17. Which means that you're going to have these horizontal lines at v equal negative 17. So there's no way that your velocity is ever going to be able to get to actually being negative 17, much less anything greater than that. So your velocity is always going to be between negative 47 and negative 17, which means that v plus 17 is always going to be less than 0. And I made a little error here. I wrote the absolute value signs here. I meant to not have those. So what I'm trying to say here is that v plus 17 is always negative, which means that if you're taking the absolute value of a negative number, you're changing the sign. So we can rewrite that as just v plus 17 times a negative, because when this is negative times another negative, we get a positive. So that has the same action as taking the absolute value. Alright, so now that I've gotten rid of the absolute value signs, I can solve for v. I'm going to multiply on both sides by this negative, and then subtract 17 from both sides. So multiplying by a negative gives me negative 30 e to the negative 2t. Subtracting 17 gives me this negative 17, and that leaves me with an expression for v. And this is true for t greater than or equal to 0. It'd be useful to go back over why we're able to get rid of the absolute value signs by writing this negative here. That's going to be a skill that will be very valuable going forward. Alright, so in part B we're looking for the terminal velocity, which of course would be the value of velocity as we are approaching big values of t. So we take the limit as t approaches infinity. Now, we notice that negative 30 e to the negative 2t is going to approach 0 as t approaches infinity. And that's because we can rewrite this as negative 30 over e to the positive 2t, right? And e to the positive 2t is going to get very, very large as t approaches infinity. So we'd have negative 30 over a huge positive number, and that's going to be approaching 0. So that means we're going to be left with negative 17 feet per second. Now, I want you to notice how we can use the slope field to also take a look at this limit. So remember that we have dv dt is negative 2 times v plus 17. Alright, so let's just draw a quick slope field. Notice that the horizontal slopes are going to occur when v is negative 17. I've drawn those here in green. Our initial condition, our initial velocity, was negative 47. So if I start here at negative 47, consider the slope at negative 47. Well, we'll have negative 47 plus 17, that's negative, times the negative is a positive. So we have a positive slope, and notice everywhere where the velocity is less than 17, we're going to have positive slopes. So our velocity curve is going to be getting closer and closer to a velocity of negative 17, but it's never going to actually get to negative 17. Here at negative 17, we have those horizontal slopes, so we can never actually quite get there, right? We're going to get infinitely close, and we can never cross over it. So if I were to draw my particular solution, it would look like this, and that allows me to clearly see the value of the limit as t approaches infinity. My value of v is going to be getting closer and closer to negative 17. So it's very helpful to use the slope field in this situation. In part C, I'm looking for the time when it is safe to land, and I'm told it's safe to land when the speed is 20 feet per second. Now pay attention to the fact that it was speed is 20 feet per second. We know we're traveling downward, so if we're traveling downward, that means our velocity is negative. So velocity would be negative 20. And when we have this set up, we're then good to go. The tricky part is making sure you have the velocity at negative 20. So setting that equal to my velocity, I'm going to now be able to solve for t. I'm going to add 17 to both sides and then divide by negative 30. So that's going to be negative 3 over 30, which ends up being positive because it's a negative divided by a negative. In fact, I could rewrite this here as 1 over 10. All right, so I have the natural log of 1 over 10. It's a little bit easier. And then I can take the natural log of both sides, and that's going to leave me with negative 2t on the left, and on the right I have natural log of 1/10. Note here, natural log of 1/10 is natural log of 1 minus natural log of 10, and natural log of 1 is 0. So on the left I have negative natural log of 10, and then I'm going to divide by negative 2. So a negative divided by a negative would be a positive, so I'll have natural log of 10 divided by 2, and that's going to leave me with 1.151 seconds. So that is the time when my velocity is at a point where it's safe to land.